Good morning, everyone. It's quite early in the morning as I record this, so it's a little bit overcast. So unfortunately, my face not be as well lit as usual, and that part of the recording may be a bit grainy. But hopefully, you can hear my voice just fine, and also see the slides that I have up on the screen, because that's basically what I'm going to be talking most about. So today, I'm going to be telling you a little bit about air columns. So if you remember from the last time, last week we talked about waves, two different kinds of waves, longitudinal and transverse, and how waves can reflect at a boundary. And those two concepts are going to be important for us today because, and also the concept of resonance, because all those things are going to be important to us today because we're going to apply them to the concept of an air column, which is really just another way of describing a musical instrument, or at least some musical instruments. Well, you'll see. So let's dive in. So within musical instruments, there are obviously a whole different variety of them, but one that makes use of, or one that can be described as an air column, are wind instruments. So for example, we're talking about clarinets, trumpets, organ pipes. Hardly anyone plays those. But the idea is that you have some kind of column, right, or cylinder, although it could be bent into a strange shape, like a trumpet, for example, and there's going to be some kind of wave inside of it that vibrates the air. Of course, you can't really have an instrument without having some kind of open end where the sound can come out of. And usually what happens in a real instrument is that you don't just get a single sound, you actually get a multiple of sounds with kind of one dominant one. Let's look at the two kinds of air columns. The first kind is one which has a closed end. So this might seem kind of odd. It's like, how can you have an air column that has a closed end? But I'll give you some more examples in just a second. So the idea here is that we have our column on the left, and the closed end is the bottom here. And so what I've done is I've drawn a quarter wave inside of the column, a quarter wavelength. It might be kind of hard, right? It's like, well, this is strange looking shape here. It looks kind of like a V. So if you were to think about this as a transverse wave with one full wavelength, if you took this shape here that I have drawn, you would see this is actually just 1/4 of the wavelength. I'm going to draw that out in just a second. So a little bit more vocabulary. The idea here is that where the wave hits the closed end of the column is called a node, okay? N-O-D-E, node. And the open end is called an antinode. So this part here is called the antinode. All right? So again, that's just a little bit of terminology. Where it's at the closed end is a node, where it's the open end is an antinode. Okay, so this has a special length associated with it. It's called L1, or sometimes called the first resonant length. And the sound that comes out of this is called the first harmonic. Musicians might also call this the fundamental mode, but I'm not going to assume you're a musician, just a physics student, so we're going to stick with the harmonic. Okay, if you then make a longer tube, right, now all of a sudden you have a shape that looks like this. Wow, what the heck is going on? Well, I want to point out that this V shape, the V shape that we started with, is now moved up to the top, and below that is what's called a loop. And a loop is actually a pretty special shape when we're talking about waves. A loop is essentially always 1/2 of a wavelength. So when you see a loop shape, you know, oh, this has got to be 1/2 of a wavelength. So we have the half wavelength from the loop, as well as the quarter wavelength that's sitting on top of it. And together, 1/2 plus 1/4 is 3/4. So that means that this shape here is 3/4 of a wavelength. In addition, you have the parts of the wave which are open, right? Like at the opening of the column, for example, the wave is nice and wide. That's again called the antinode. So we have two antinodes, and where the wave kind of crosses over, where the wave is narrow, those are called the nodes, right? So again, we have a node at the closed end, and we have a node kind of between the loop and the little quarter wavelength. All right, so notice the pattern here. It always seems to go antinode, node, antinode, node, and that's not by accident. That's actually how it always goes. So this length we call L2, or the second resonant length. And you can see that this can actually continue on. We can keep on making longer and longer tubes, and again, all we're doing at each case is we're just adding on more of these loops. So this one is called, the length here is 5/4 wavelength, and this is called L3, or the third resonant length. Okay, so let me just back up a second here, because I'm using this word resonant, and this goes back to last week's lesson about resonance. What's actually happening inside of this tube is that we have a wave, a sound wave, which is resonating or vibrating at a very special frequency or at a very special wavelength, so that it actually sets up sympathetic vibrations with the tube itself. And so at any other frequency, you would basically get almost no sound out of the tube. But at these special resonant frequencies, then you get an amplification, or you get a loud sound, right? And this is why when you're playing a musical instrument, you can't just play any old note. You have to play very specific notes, which usually correspond to different fingerings and so on, depending on what kind of instrument you're playing. You're closing different holes and making the length of the tube very particular. All right. Okay, I'm going to pause there for a second because I just want to jump over to a little bit of a sketch, because I want to talk about this a little bit more, because this can be very confusing if you don't see a little bit more how this is constructed. So just 1 second here. So the idea is we want to fit wavelengths into this tube. The thing is that this right here is a boundary, right? This is like what we talked about last week. So this is where the wave has to reflect from. And this is where the wave is going to come out of, okay? So if you remember the way that I was drawing transverse waves last week, the transverse wave...
2,000 years later.
Okay, so our wave had its equilibrium line like this. A little more straight, but you get the idea. And we drew a transverse wave where it went up and down and back again. Okay, so the idea is this looks very different from the picture that I had just a moment ago, because the picture that I had a moment ago assumed that this wave is reflecting or vibrating with itself, right? It's reflecting back on itself. So the idea is that if we had a boundary here, this wave is going to reflect back on itself. Sorry, I can't have it. Yeah, if I have a boundary here, this wave is going to reflect back on itself. So in other words, and if you remember from reflections, if this wave comes in at a hard boundary, it reflects back the other way, right? It reflects back, in this case. All right. All right, something like that. So the idea is that this wave is reflecting back on itself. Now, what I'd like to do is I'd like to somehow fit this wave into this tube. And so this end of it has to have a node here, right? And in the way that I've drawn the wave here, it has 3 nodes, 1, 2, and 3. So one node has to be at the hard boundary here, right? The fixed boundary. However, if I want to actually have a loud sound come out of the tube, then I have to have where the amplitude is largest. That's the amplitude basically corresponds to the volume. So in this case, the smallest wave that I can fit into a closed tube is one where I have a node here, and I have an antinode, which is the wide part at the opening, right at the mouth of the tube. So that looks like this. All right, something like that. Now, how many of these shapes are in this one? Now, again, I didn't draw it particularly well, but keep in mind that this is one wavelength, 1 lambda. 1 lambda is this characteristic shape, right? Like up, down, and back again, right? That's one way. What's the 1 lambda? And I've just reflected it back on itself to get the full full reflected wave. Okay, so this is 1 lambda. And I want to figure out, well, how many of these are in here? So if I just switch my pen to maybe a different color, let's go red. Good. All right, well, there's from the node to the antinode, there's 1. And I could also go from this node back, there's 2. And then if I draw another line here, from the node to the antinode, that's 3. And then from the node to the antinode is 4. So there are 4 of these. There are 4 of these shapes in a full wavelength. So that means that if there are 4 of them, then that means that this shape is actually 1/4 or 1/4 of a wavelength. Okay? So when we're doing these kinds of problems, all you need to do is basically count up these shapes. And each one of these is going to be 1/4 of a wavelength. Okay? So in this case, another thing that kind of makes your life easy is to look out for is these things are called loops. Okay, I call these things loops. And a loop is always equal to, okay, a loop is always equal to 1/2 of a wavelength. Okay, loops turn out to be pretty important, especially when we talk about open air columns. But we'll get to that in just a second. All right, 1/2 a wavelength. Okay, you get the idea. Okay, so remember this shape, right? This is the loop. And remember this shape. Okay, this is half of a loop, which is the smallest that you can have for a closed air column. All right. This is why we have this shape is 1/4 of a wavelength. Here we have a loop that's 1/2 of a wavelength plus the half loop. So I have, so again, if you count the half loops, you have 1, 2, 3, and each of these is a 1/4 wavelength, so you have 3/4 of a wavelength. Here, if you do the same thing, you have 1, 2, 3, 4, 5. So that's why this one is 5/4 of a wavelength. Okay, the story changes a little bit if we have an open air column. Okay, so an open air column is one which is open at both ends. And whenever you have, and the ends, right, the ends is where the sound comes out. So those are always where the amplitude is greatest. So those are your antinodes. And in between the antinodes is a node. So again, if you look at this shape here, you can see that it's 1, 2, 2/4 or 1/2 of a wavelength. Okay, so for the open air column, this one is the first resonant length. If you make the tube a little bit longer, then you can fit in 4 of these, right? So 1, 2, 3, 4, that's 4/4 of a wavelength, or in other words, 1 complete wavelength. Okay, that's the second resonant length. If you make the tube a little bit longer, and again you count, you go 1, 2, 3, 4, 5, 6, 6/4 or 3/2 equivalently of a wavelength is what will fit into this tube. So we're just making the tube longer and longer. And you might wonder how we could do that, but actually there are many musical instruments which actually allow you to either make the tube longer as you play or are just a collection of different sized tubes. So that's the third resonant length. So basically this is the first resonant length where you have 1/2, second resonant length where you have 1 full wavelength, and the third resonant length is where you have 3/2 of a wavelength. Okay, so let's try and figure this out with a worked example. So in this case, it says, in an experiment to determine the speed of sound, a 220 hertz tuning fork, so meaning that this tuning fork, if you were to like knock it and play a sound, it would be 220 hertz. That's the sound that you would hear. Is held over an open air column, open at both ends. If the first resonant length is 0.76 meters, what is the speed of sound? Okay, so I'm going to switch over to my other thing. Just want to make sure I have all the numbers right. And so in this case, I'm going to apply the universal wave equation, which is V equals f lambda. Okay. Now in this case, it says to calculate the speed of sound. So speed is still v, right? Just like it has been since the beginning of the course. F is the frequency of the sound. So in the question, it said I was creating a sound of 220 hertz. So 220 hertz is going to go there. All right. And, okay, that's different. And the wavelength, it said the tube was 0.76 meters long. 0.76 meters long. And it was the first resonant frequency. So that means that in an open air column, if I just do a little sketch over here, it's probably going to be kind of gross. The idea is that this, oops, is my tube, and this is one loop, right? This is one loop. This is the first resonant length in an open air column. Okay, so that means that my length, so my length here is half a wavelength. Or if I just move this around, or manipulate this, I have that wavelength equals 2L. Okay, and the L was 0.760 meters. Okay, so in order to get the wavelength, which I need for this problem, I'm going to take this number and put it into there. Okay, so my wavelength in this case is going to be 2 times 0.760 meters. All right, and my last step is just to multiply all of this out. And if I do that, then I get 334 meters per second. 334, should be 334. 3 significant digits. Okay, let's call this, let's say that's 3 significant digits there. Okay. All right, so what kind of makes these questions tricky is not so much plugging the numbers into the formula, really. It's knowing what numbers to put into the formula, specifically what number to put in for the wavelength. That's actually the hardest part. So that's why if you see over here, I often just do a little doodle on the side so that I know what is happening inside of my tube, so that I can use a relationship between the length and the wavelength to, because it's really my wavelength that I need to put into the equation. So if you ever play a musical instrument and you look at the sounds coming out of it, you'll see that there's something called harmonics produced. And harmonics are basically additional frequencies that get played along with the fundamental, or the first resonant frequency. So a moment ago, I was talking about different sizes of tubes that can produce different sizes of tubes that can produce resonance. Well, in this case, you can actually have the same size tube, but it actually produces more than one resonance. And those different resonances are called the different harmonics. So the idea is we're not going to change the length of our column, but just because of the fact that we're blowing sounds into it, it's just naturally going to produce more than one sound, and that's just typically how it works. Now you might think, well, that's kind of frustrating, but in actuality, it's kind of what makes musical instruments sound the way that they do. If you just had a single frequency, like if your music teacher says play, an A or something, like, yes, you're going to play that A, but you're going to have other sounds that kind of make the A sound richer. And if you didn't, then your instrument just wouldn't have the same quality of sound. Okay, so So the idea is one thing that so you can do this a couple different ways. Again, for those of you who play musical instruments, you may know that if you have your fingers in the same orientation, right, the same fingerings, and you blow harder into the instrument, then you'll quite often produce a higher pitched sound, right, a higher frequency sound. So that's one thing that that could be true. So let's just look at how these harmonics work. I'm going to start with the open-end column. So in this case, we have the first harmonic, like we did in the last problem. But then if you keep the tube the same length and you blow harder, right, this is one way to do it, you can actually fit more wavelengths into the same length of tube. So this is how that looks. So from the first harmonic, you have, again, count these V-shaped thingies. So we have 1, 2, so this is half of a wavelength here. And in the second harmonic, I have 1, 2, 3, 4. I have 4 halves, or sorry, what? Yeah, sorry, I have 4, not 4 halves, 4 quarters. Well, okay, let's try that again. Okay, so so if you look at this open-end tube, you can see that it has 1, 2 of these shapes, right? And each of these shapes corresponds to a quarter of a wavelength. So I have 1, 2, 2 quarters, or 1/2 of a wavelength, right? That's the first harmonic. That one's simple. It always works that way. And then if I blow a little harder into the same length of tube, then I get 1, 2, 3, 4, 4 quarters, or 1 complete wavelength. This might not look like 1 complete wavelength but in this case it is. It's just we're starting again always at the antinode, because the antinodes have to be at the open ends. And then if I blow a little harder still, then I get 1, 2, 3, 4, 5, 6. I get 3 halves of a wavelength. Okay, so again, it's very similar to what I was talking about before, but in the case before, we were actually making the tube longer. We weren't blowing any harder, we were just making the tube longer. But in this case, what we're doing is we're keeping the tube length the same, but we're, possibly blowing harder, or possibly putting in a higher frequency. There's a couple ways to do it. So different frequencies. So these different shapes will correspond to, if we keep the speed of sound the same, right? We're not blowing any faster. Then these 3 frequencies, these 3 resonances will actually be 3 different frequencies, 3 different notes. So if we take, for example, this one, so this is our first frequency of 440 hertz, let's say, a musician would call this the fundamental, but a physicist would call this the first harmonic. So we're just going to stick with the first harmonic. So this is my first harmonic. And then this one, the second harmonic, is just double the first one, right? It's the second harmonic. It's literally double. That's the mathematical relationship between them. So this one is twice the frequency, or 880 hertz in this case, right? That's called the second harmonic. And for the third harmonic, this one is just triple the first harmonic, right? 3 times the first harmonic. So there's a beautiful mathematical relationship there. It's very simple. As long as you can, multiply by integers, you're good to go. Okay, so let's just look at another example. On a cold, frigid day, Matthew blows on a toy flute, causing resonating waves in an open air column. The speed of sound through the air column is 336 meters per second. The length of the air column is 30 centimeters. Okay, calculate the frequency of the first, second, and third harmonics. All right, that doesn't sound so bad, because we have the length, we have the speed of sound, and so all we need is the frequency. I think we can do this. All right, so the first thing we're going to do is, well, we can write down our numbers, I suppose. It said the speed of sound is 336 meters per second. All right, and the flute was 30.0 centimeters long, so I'm just going to convert that to meters straight away. So 0.300 meters. All right. So now notice that this is the length, not a wavelength. So what's going to happen is we're going to convert this length into a wavelength in short order. And what I'm trying to figure out here is F1. Okay, once I know F1, then I just need to multiply it to get F2 and F3. So here's my picture again, right? Here's my open air column. This is the flute. And this is the first fundamental inside, right? Antinode, antinode, node, antinode. All right, just like that. And I have one, two of these V shapes. So that means that my length is equal to 2/4 or 1/2 lambda. All right, I'm able to fit 1/2 of a wavelength inside of this tube. So again, if I just manipulate this, then I have that lambda equals 2L. All right, just like that. And so now I have this mathematical relationship. I know what L is, I know what V are, and I can use my universal wave equation to figure out my frequency. So in this case, I'm going to start with the universal wave equation, V equals F lambda. So F, just divide both sides by lambda, so I have V over lambda. But using my earlier result, I actually have V over 2L. So equal to 336 meters per second divided by 2 times the length, which is 0.300 meters. All right, just like that. And if I put that into my calculator, I will get a frequency. Sorry, this is F1. I will get a frequency of 560 hertz. Okay, good enough. Now, the question is, how do I go from this to calculate F2? I don't want to go through the whole thing. I don't want to go through all this calculation again if I don't have to and draw a little doodle and all that sort of stuff. Instead, I just want to use the relationship that F2 is just 2 times F1. And so then I'm just going to go 2 times 560 hertz. Okay, and work that out. And I get about 1100, 1120. Okay, cool. And same thing for F3. This is going to be 3 times the first harmonic frequency. So yep. So 3 times that. It's going to be 1680. I did that right? Did that in my head. There we go. Okay. And so that's it. So again, most of the work is done just getting the first frequency, the first harmonic, and then from there you can just multiply by the appropriate integer to get the second and third harmonic. Okay, so just check our answers, and yes, they are correct. Good. Okay, so the same thing can be done with the harmonics for a closed end, but there's one little wrinkle here. So again, we're not going to change the length of the tube. We have our first harmonic, and this one only has 1/4 of a wavelength in it because, again, we have to have a node at the closed end and an antinode at the open end. And then the there is no second harmonic. Oddly enough, there is no second harmonic because, again, the number of the harmonic in this case goes with the number of quarter wavelengths. In this case, I have 1/4 of a wavelength. And in this case, I have 1, 2, 3. I have 3/4 of a wavelength. So because, again, we want to maintain that mathematical relationship, this one is going to have 3 times the frequency of this one. So that's why we call this the third harmonic. There is no second harmonic. There is no way to actually get a full wavelength inside of this. Sorry, there's no way to get half a wavelength inside of this tube. It's just impossible. So the next one up would be the fifth harmonic, where again you have 1, 2, 3, 4, 5 of these quarter wavelengths. So the mathematical relationship between this one and the first harmonic is this one is 5 times. So it's the fifth harmonic. So yeah, it might seem kind of odd that you can have a second harmonic for an open-end column but not for a closed-end column, but it's the simple physics of the wave having to reflect at the fixed boundary. Okay, that is the closed end. If that weren't there, then we could have a second harmonic, but if that weren't there, we'd have an open air column. So a different story. Okay, so there it is. So again, if we just talk about our harmonics, we're not going to worry about this fundamental mode stuff, although maybe if you're like a musician, you might care. But in this case, we're just going to call these the first, third, and fifth harmonic, and the mathematical relationship goes the same as for the open air column. Okay, I'm not going to do this example. Sorry, you can look at the slides. So I'm just going to, so this is just basically a summary. Again, this is the open air columns. This is the closed air columns. The open air columns always have antinodes on the open ends and a node in the middle, or I should say a node between antinodes. So as you add on more antinodes, you're going to have more nodes, right? And same kind of deal for the closed air column, except that one side always is going to be a node, right? That's the closed side. The other side is always going to be an antinode. And then in the middle, you could just add additional nodes and antinodes as the case goes. All right. So that's kind of it. That's kind of how standing waves in air columns, roughly speaking, work. For those of you who are musicians or maybe listen to music, there are lots of musical instruments that correspond to these air columns. You know, I mean, there's such a variety of musical instruments and such a variety of shapes, but a lot of them can be simplified down to air columns. So there are certainly ones that correspond to open air columns and ones that correspond to closed end columns, or columns closed at one end. So for example, here's an organ pipe. So if you were to go into a church, for example, you might see an organ pipe kind of like this one, where all the pipes are different lengths. So the different lengths correspond to the different notes that it can produce. And an organ pipe actually has 2 open ends, right? There's the open end here, and there's the open end here. So this is basically the length of the tube between those 2 open ends. However, a flute, similarly, is an open end tube. So in a flute, for example, you have this open end, and you have this open end where the musician will blow across this hole. So essentially you have 2 open ends there. Whereas a clarinet is definitely closed at one end. So in this case, this is the reed. So the player closes this end, basically, I mean, just barely wide enough that they can get air into it. And this end is the open end. So a clarinet would correspond to a closed end tube. Okay, so in summary, just quick summary, a closed air column is going to have an antinode at the open end and a node at the closed end. And for an open end, it's going to have an antinode at each end. All right, so I'm going to ask you to look at worksheet 8.4.2. A couple of problems there. I think I'm gonna take a look at that worksheet and decide on a couple problems for you to do. And then once you're done that, come back here later in the week, and I'm going to have a video that's going to give you some data that you can use for a lab. Okay, so check that out. I'm not going to have it ready for Monday. This one is going to take a little bit of extra work. So check back here later in the week, and you'll see it then. Thanks. Bye.